this session will be recorded, and by attending this meeting you consent to that being recorded. If you make comments or you come off mute or you share your camera, your image and your words will be recorded. Thank you everyone for joining today. It is a pleasure to be here. I'm visiting from a Wawakal country, which is in Lake Macquarie in New South Wales, and we'll do a acknowledgement of country a little later on. I'm Gavin Cross from CSIRO. We are the official knowledge sharing partner for this project, and it's our pleasure to host this session as the knowledge sharing partner. It's fitting that I'm here today in Alice Springs in the Desert Knowledge Centre, the Desert Knowledge Precinct at DKA, to share this roadmap that we've been working on, the Alice Springs Future Grid roadmap to 2030, and this is the public briefing. This is an official deliverable for the project, and we'll talk about the funders. Other knowledge sharing content for this project is on the ARENA website under this project, and you can look those up in the knowledge sharing bank on the ARENA website, such as technical plans, lessons learned, and other reports that have been published. This session will be recorded as I noted, and it will be published and shared as a part of the project. And the release of the document will come out later, and Lyndon will talk about that. So the session today, you'll hear from Lyndon Pearson, the project director, and we will have some questions and answer session as well. So what we'd like to do is undertake the presentation followed by Q&A. I have enabled the Q&A on the chat, so you can put your questions in there and we can address those. If you have any that are coming through as you see this presentation, please note them. And any of the questions that come through may form part of an FAQ that could be developed after this project briefing as well. So any that we may not be able to answer or are answered within the report, we will take on notice, and many of the technical details will be dived into in the actual roadmap document. So it's my pleasure to have been involved in this project from the start, and we're pretty much right at the end now. So this is a capstone deliverable of the project. There's a number of consortium members and partners and individuals that have provided input into this, and it's really important that we're able to share these learnings and what we've developed as part of this this project and what is the roadmap to 2030 for Alice Springs. So at this point in time, I'd like to hand over to Lyndon, who's going to take you through the presentation. Just to remind everyone to be on mute, please, and please direct your questions through the Q&A. Thank you. Lyndon.
Thank you, Gavin, and thank you everyone for joining us, especially those of you on the eastern states who've joined at 5 p.m. as you would otherwise be preparing to go home. It really is exciting to be here today and to share with you the work that we've been doing as part of Alice Springs Future Grid. This is a project that has had a long gestation period. It was built off a legacy of decades of work that had occurred in Alice Springs from a range of different people that had got us to the point where we started this. We started trying to get the project underway smack bang in the middle of COVID, and it is somewhat ironic, but perhaps a sweet ending that at the very end of the project, there are people we'd had hoped to have in face-to-face today. They're not able to be because they're at home sick with COVID. So it has been a project that has been framed very much by the circumstances we've all lived through over the last couple of years. But as we meet together, I think it is really important to recognise that this is a project that is fundamentally bounded by place. And in being bounded by place, its connection to the land on which this project is built. This project has been facilitated by Desert Knowledge Australia, who manage and as a statutory entity of the Northern Territory Government, manage the Desert Knowledge Precinct. The Desert Knowledge Precinct hosts the Desert Knowledge Australia Solar Centre, one of the preeminent research and learning facilities for solar research in the world. but it's located on land that exists under an Indigenous land use agreement that deliberately seeks to bring together parties together to work and to collaborate. And I think then that the welcome to country for this project is even more poignant because it is a project that, in acknowledging the Aranda people on whose land Alice Springs sits, we're acknowledging also that it was Aranda people who gave forward the land on which the project is physically operating under an Indigenous land use agreement, with the explicit expectation of people coming together as a meeting place and working together. And that's what this project has been all about. So in that context, I would like to acknowledge the traditional owners of the country on which we meet, their elders past and present, but also the elders past and present from all the land on which different parts of the project team have been based over these last few years. So what is Future Grid, and why is this relevant, and why is it relevant that you're here today? The project is a consortium project. It's a project that fundamentally brings together a whole group of people, a group of different entities: Desert Knowledge Australia and the Inchalum Centre for Future Energy, Acustica, Power and Water, Territory Generation, Desert Knowledge Research Institute, CSIRO, Jacana, and Arid Lands Environment Centre. The consortium partners came together and all have made significant contributions to this project, CSIRO coming forward as the knowledge sharing partner, and Jacana and ALEC as key sub-project leads in the project. We also have a range of other project participants, be they RMIT or CDU, ASO Automation, Redback, Grid Cubed, the variety of different suppliers who've been able to support the project as we've progressed. But a project like this would not be possible without direct funding. We have been very fortunate in this $12.5 million project to receive $8.5 million of cash in a contribution from Australian government through DISA and through ARENA, as well as nearly $3.5 million directly from the Northern Territory government that was funded via the Inchalum Centre for Future Energy. Telling you who the project is interesting, but it's really what the project is about. And the project was fundamentally a systems project. It was born of the recognition that the challenges we were going to be facing in the years ahead would require a different way of thinking and a different way of project partners and participants in the power system from engaging with each other compared to the way they had in the past. It's not a judgment on where we may have been previously, but just reflecting that the power system is changing, and as a consequence, the relationships of the entities within that system must necessarily change. And so we put together a system project. In many ways, nothing or very few of the things that we've done within this project are actually that new. Many of the things that we've done have been done by other entities. Many of them have been done by projects funded by ARENA. The difference with this project, and what I think makes it so critically important that we're here today to share about it, is that we brought all of those things together and did them as a system. And so we started to see how the different elements of those technical and commercial trials actually interfaced with each other. So the project as a whole had consisted of 5 broad themes. The first one was modelling. A lot of focus on both power system modelling, but also techno-economic modelling, and looking at different ways of understanding how the power system actually operates in this future state. Sub-project 2 was all about understanding the role of self-islanding grids, and particularly the role of grid-forming batteries, not just in their ability to disconnect from the grid, but how they can act as an active participant, an active facilitator of grid services within the broader network. Sub-project 3 really focused on understanding community aspirations and community connection into the future of our power system through things such as virtual power plants, but also through working to community surveys and other activities to better understand community role and community sentiment towards the power system. Sub-project 4 was very much focused on the commercial side of the power system of the future, thinking particularly around tariff structures and how those tariff structures might be aligned to differing models of behind the meter and distributed generation within the power system of the future. And finally, sub-project 5 was very much focused on what are the enabling pieces of infrastructure that are required to be able to support and facilitate that power system of the future. Why Alice Springs? It's very simple. Alice Springs, through a bit of a quirk of history, is a discrete microcosm of the NEM. We have a centralised system controller. We have, which is governed under independent legislation and is auspiced by AEMO. We have a set of national energy rules. We have a network operator whose operations and costings and charge expenditure and capital works are all governed under the AER. We have competitive retail and generation and operating with an open access regime. Whether those things are good or bad is sort of a subject for other people to discuss, but the reality is we carry all of those characteristics in Alice Springs. So we are in many ways unique in that we are a small grid. We're an isolated grid, and we're small enough that small changes can be seen and observed very rapidly. But we're small enough that we can undertake trials that then have national significance. The work we do here in Alice Springs is not just for the benefit of Alice Springs or indeed for the Northern Territory. It is for the benefit of Australia because the lessons learned here have carriage throughout the country. And it's for that reason the Commonwealth was able to make such a significant contribution into the work we did. We'll get a little bit more into what Alice Springs looks like and how's it working. But I think it's really important to understand that everything we talk about today is coming from a system perspective. There'll no doubt be some people who wish to see particular areas and particular interests more focused on in any discussion around a roadmap. We, however, have always been very clear that the roadmap objectives must be at a system level. So the roadmap set out to map out a number of credible scenarios for what the future of the power system would be. They had to recognise that consumer engagement and customer participation was materially changing, both in the adoption of distributed PV, but also in what consumers were expecting from the power system. The reality is that consumers, regardless of their desire for integration of PV or EVs at home, they still expect, in fact, that not just they, we all expect a secure and reliable outcome in the power system that we engage with. We recognise that in the roadmap, it wasn't just trying to work out what the future might be, but also to recognise at what point does our existing trajectory become untenable. Sadly, much of our discussion around energy transition comes from a view that things are linear and stepwise, not always understanding how the decisions we make today in years to come may prohibit the step changes that are actually needed in the future. And so in many ways, we've used language of transformation rather than transition, recognising that transformation means that things are materially changing, but we need to do that in an orderly manner. We built out the roadmap with a view to being able to shortlist solutions that focus on urgency and ambition, but also in coupling with that a least regret pathway, knowing that we didn't want to be in a position that we were making all the decisions for 2030 today, but making sure that we didn't exclude decisions today that would limit future opportunities. That way, we allow the greatest possible opportunity for different participants to have influence over that pathway to 2030. Really, really critically, the roadmap for 2030 that we've put together as part of the Future Grid is not a recipe book. It doesn't give you a clear set of instructions. It's not an IKEA manual that just says take part B and add to tab C with screw D. What it does is it seeks to understand the boundary conditions of what's possible, establish what is likely or plausible, and then provide information around how to get there. The structure of the roadmap is reasonably simple. Looks at where we are, what and how things are changing around us, where we're going, what is changing, and what are the opportunities that actually exist out there, and then what are the actionable pathways and the near-term actions that we need to take in order to implement that. And today I'll talk you through each of those different sections. So how has Alice Springs been powered? For many of you, this may be very simple and already well understood, but it's not necessarily fully familiar with many of the people who think about what Alice Springs actually is as a power system. Largely, it has been like most power systems around the country, one-way power flows, principally driven by natural gas. And we're very fortunate here in Alice Springs to have access to pretty abundant supplies of natural gas that have served us well over many years. Our total generation contribution of centralised generation is about 87%, with that coming from the primary gas generation that I mentioned previously. We have centralised renewable generation contributing to 4%, which is primarily a large solar power plant, the Eterno Solar Farm, that was commissioned in 2012 and then further expanded in 2016. And then 9% of our generation coming from behind the meter distributed PV. That's coming from a base of 0 in 2008 when Solar Cities was launched. In 2008, there was 2 grid-connected PV systems across the entirety of the territory, and our Solar Cities was a key enabler of being able to grow that. The 9% doesn't sound like a lot, and certainly in the context of the national energy market, where percentages are considered to be a lot higher, the 9% seems low. But when we start to dive into the detail a little bit further, we start to realise just how far Alice Springs has actually progressed. While there had been some increases in aggregate demand leading up to 2015, a noticeable trend emerged from 2015 through until now. And that is, looking at the graph on our left-hand side, a material and sustained reduction in the measured centralised system demand. So this is the system demand that is actually placed on the generators at Alice Springs and Rongoodin. And you can see that that has been a material decrease from 2015 to 2022. This decrease is not explained by population changes or energy efficiency. What it's largely explained by is the significant growth in behind the meter generation. One of the key consequences of that is that daily load profiles are hollowing out in the middle of the day, typically in that period of 10 a.m. to 2 p.m. For those who are familiar with the language used elsewhere, the duck is alive and kicking in Alice Springs. Sorry, as noted, the lurgy has been knocking a few of us out, so my throat was just getting the better of me at the end there. But yes, the duck curve is very present, and that has some material consequences for what we're doing here in Alice Springs. The power system is changing as a consequence of decarbonisation through energy policy, and that can be explicit decarbonisation activities, or it can be more general energy policy supporting renewables. We've had significant changes in the decentralisation of generation sources, and that's really tied to that changing of customer expectations and community expectations. And it really is reshaping that view of what the power system is expected to be. When we start to look at that more deeply, we see that community expectations around a safe and affordable power supply have materially changed. Through the work of the Alice Springs Future Grid, we really mapped out 8 key values the community members continue to say they valued when they considered the future of the power system. They, of course, expect it to be dependable. We all want our power system to be safe and secure, and we want it to be affordable. It has to be efficient and it has to be cost effective compared to the alternatives that we want. But so many of us are aware of the sustainability of our power system, and it needs to be able to support the 2030 and 2050 decarbonisation goals. But there's also a strong sense that in whatever we do about those goals for the future, it has to be able to ensure that there's equitable access to the benefits associated with those changes. Equity was a really strong message that came through in all of the work that we did when we engaged with the community. It has to empower. It has to be able to facilitate consumer agency in the work that they do. The consumers need to feel as part of the discussion. And very often the conversation that we received back was consumers felt like they had been ignored or not considered when decisions were made, and so therefore went out to make decisions themselves. It has to be able to expand. As much as this base system system demand is declining, as I communicated earlier, we do recognise that growth in electrification will change the nature of our power systems. But it's not just the electrification of our power system. The reality is that air conditioning load or heating and cooling load in places like Alice Springs are increasing demands, as well as the electrification of industrial processes. So it has to be able to accommodate that expandability into the future. And by extension, it needs to be adaptable. It needs to be able to respond to change and be able to adapt to a power system where the technical solutions are moving rapidly. And fundamentally, underneath all of that is a foundation of it needing to be beneficial. The community needs to recognise and to be able to value and trust what the power system and all of its participants are actually seeking to do. If it's not seen as being broadly beneficial, then its relevance and its ability to influence the community significantly deteriorates. There's a lot of fluffy words there. In many ways, those words are not words that are traditionally associated with engineering views of the power system, but they are important because fundamentally the power system is there to serve consumers. We spent a lot of time talking to consumers through the power system. We saw that through both targeted surveys, broad-based surveys across the community, and then one-on-one interviews, common themes continuing to emerge. Significant uptakes already in Alice Springs, where nearly 50% of houses already have solar hot water. We have nearly 55% of people wishing to invest in batteries, solar and batteries, if they haven't got them already. We have one of the highest densities of rooftop PV already here in Alice Springs. Granted, many of them are older and smaller systems, dating as far back as the Alice Solar City program. But there is significant support underpinning all of that and significant expectation of government to drive a progressive development of renewable energy in Alice Springs. But they do recognise that there's barriers. Price is a key one, both price of componentry and the sensitivity to that, and particularly in an economically constrained environment such as we're living at the moment, but also recognising how rebates are accessed, but importantly, who is actually benefiting from those rebates. And a really strong piece of work came out of the analysis that we were doing and the community consultation that was coming is around the extent to which people who are renting, be they in public housing or in private sector renting tenancies, were not able to benefit from the broad-based uptake of renewables. And so these were areas where consumers kept coming back and saying, we don't really care too much about this technology conversation. We don't really care too much about minimum demand, but we do care about this outcome and we need that to be heard. So we took that on board and we gave thought to, well, how does that influence the thinking that we're going to need to have in the development of this roadmap? Notwithstanding what the community wants, there are material operational challenges. As I mentioned before, that duck curve is alive and well. We have got increased system volatility and we've got that declining operational demand. On the right-hand side of this page is a graph of a load that was mapped out on 9th of October last year. I know that this was a scary time for a lot of people because I was getting phone calls at home from various senior people within government and elsewhere worried about what the consequence of a minimum demand of this level actually was. This was the third minimum demand event we'd had last year, and we've actually in 2022, and we've had subsequent events which have encroached on this record low again. Getting down to 5.67 megawatts demand may not seem like a lot to many people, but in the context of our power system, it is really, really troubling to think about how we keep a power system stable at that point. The engines that we operate here in Alice Springs are not able to operate at levels that low. Now, sure, if you had a 10 megawatt engine and you had 5.67 megawatts of load on it, that's fine. Then the generator should be able to operate stably. But we have minimum obligations within the power system to keep a set number of engines online at all times. And if all of those engines are sharing that 5.67 megawatts of load, and they also have to be able to deal with a peak load that gets up to over 65 megawatts at other points in the year, then suddenly those engines are running at the very low idle. At that point in time, the capacity of the power system to respond to change is significantly reduced. Fortunately, we have been able to operate through these periods over the last 12 months, and we've been able to do that through the hard work of men and women in Power and Water and TGen who've been worrying and sweating tears about what this minimum demand would actually do. But this change is changing our assumption around how the power system operates, and it's really critical because it's occurring in an environment of changed consumer expectation. And we see that in this next graph, or this next series of graphs. On the top left-hand side, we see a graph that shows in the blue line the historical PV capacity, behind the meter PV capacity in Alice Springs. So that's now got to about 22 megawatts. We've mapped out 3 different scenarios: low, moderate, and high uptakes over time.
Presentation. As we're talking. It's
Mr. Rodden, you may wish to go on
presentation.
Sorry for that interruption. We've mapped out 3 different scenarios looking at low, medium, and high continued uptakes of behind the meter PV. When you map those out and you look at the graph immediately below that, you see that in very crude numbers, despite the connection of a large industrial load that is due to come on in 2024, where we see an uptick in minimum demand, which is the line that is shown on the blue line the line on the bottom left-hand chart is showing the minimum demand over time, and you can see that blue line drops down to just below 6 in 2022. Even under our moderate case, we see demand dropping to negative in the middle of the day by 2027. 2028, in that period. Under the high uptake, we see it dropping below 0 by 2026. And even in the low PV uptake, we see demand sitting only just above the minimum demand that we've already experienced by 2030. Now, why is that a concern? Well, the chart on the right is the chart of a chart that's been produced by AMO, and it maps out what in blue has been the actual installed capacity per year each year since 2009. All of the colours show what the forecast was for the build out in the subsequent years. So you can see that in 2009, they were forecasting, and 2009-10, they were forecasting the build out for 2011 and 12 was only going to be 500 megawatts a year. What we have seen every year, pretty much for the last, well, and certainly since 2016, is every year we have forecast a decline in behind the meter installed PV capacity. Every year, consumers have said, no, we want to install more. Now, granted, the chart on the right is a national chart and it is showing national trends, but it speaks to the fact that consumer demand is changing and consumer requirements are changing. And so to hope that we can plan for a power system that is predicated on low uptakes of behind the meter PV seems to us to be flawed. It doesn't mean that it's not possible, and it also doesn't mean that it's not even plausible, but it does mean that we can't develop a roadmap that the entire basis of the roadmap is contingent upon assuming low levels of behind the meter PV uptake. We have to anticipate that there will be continued and sustained pressure on that minimum demand as a result of continued uptake from behind the meter solar. What does this mean? It means that business as usual is under threat. As much as this project was developed with the expectation of being able to support the Northern Territory government's objectives of 50% renewables by 2030, and that was the basis upon which we received the funding for the project. The simple reality is the business as usual is under threat now, not under threat by 2030. Some of you may have seen this chart before. It's been adapted out of work that was originally done by the Pacific Energy Institute and has been further integrated into AEMO's roadmap work. It recognises that we, over time, as we move the power system from 20th century power system capability, we've moved through a transitional period where we've effectively substituted 1 megawatt hour of fossil generation with 1 megawatt hour of renewable generation. And for a period of time, that has been effective. And that's been effective probably up to that 30% renewable energy. But what starts to occur is that you get to a point in that transition where the conventional power system is no longer able to accommodate that substitutional basis. It's no longer able to swap 1 megawatt hour out for 1 megawatt hour in, because the network is changing, the power system is changing around that. And what that actually means is that the expansion of the power system and the expansion of renewables into the power system gets to a point where step change in the system is required. And we can see that by the blue line on the top right hand side, where actually that's where we cross over from being in a substitutional or transitional environment to being in a disruptive or step change environment, which takes us to the next generation of the power system. The power system in Alice Springs without that step change is going to be struggling, because when you start to map out where we are on these things, you start to realise that actually, while the national energy market is in that critical decade of transition, and many people are talking about that right now, and Darwin-Catherine system is right at the threshold, Alice Springs, by any measure, is well now into that step change environment where business as usual is actually not just no longer viable, it's actually damaging to the position that we ultimately put customers in. Because if we just keep putting renewables in now, it will actually degrade the quality of the supply that we're able to provide into the future. To be clear, we're not suggesting the power system's that we're going to go blackout in Alice Springs right now, but we are flagging that we can't keep going the way we're going and just hope that it'll sort itself out. This is not anyone's fault. There's no one entity that we can sit here and say, well, if they'd done their job properly, it wouldn't be like this. It's a combination of change at a structural level, at a technical level, at a regulatory and an institutional level that is being driven by consumers. We are where we are, and the question of the roadmap is what we do about it. So what might the power system of the future look like? Well, the project undertook a whole bunch of different activities. We actually put in SODARs in Alice Springs and looked at the opportunity for wind to be integrated into the power system at Alice Springs. We did identify that while the wind resource here is not particularly great, both as a result of having lower wind resource than elsewhere around the country, and higher costs to develop. I think there's people need to go on mute again because we're getting some echo. That there is a complementarity to the wind resource in Alice Springs, which means that it does produce slightly higher levels of generation later in the day, coincident with the decline in solar in that late period, and that provides some potential benefit for it. And there's a part of the work that we've done. We've released a paper that looked at what that might consider and how that might work in partnership with solar and battery deployment within the Alice Springs grid. We also undertook a significant body of work around developing dynamic operating envelopes for the power system that were able to look in real time as to what the grid needed and to proactively enable or disable export from the grid, from individual people's power systems, so that we could get the full benefit from all of the behind the meter PV and batteries that are integrated in there. This trial yielded significant benefit and showed exactly how well this type of technology could work, but it also showed some of the challenges of that implementation. We undertook a fairly substantive VPP trial, some of you may have been aware of, that showed some of the sensitivities that were emerging around the integration of batteries, tariffing models that needed to be completely rethought from the way they had done previously to be able to support optimized discharging and charging of the batteries. One of the things that became apparent was that either without good tariff alignment and without things like the DOE, we could get circumstances where batteries are actually making the power system less secure by charging too aggressively in the morning and then not being able to discharge at the right times in the afternoon. And so there's a whole body of work that was taken into that and some key lessons that emerged through that piece of work. The balance of the project identified other critical enabling technologies, including the integration of grid-forming inverters, a lot of work around protection system analysis and flexible resources, both in their management but also in their forecasting and building towards probabilistic forecasting. Underpinning all of this was a realization from any of us who'd worked on the project of just how substantive the integration challenges of all of these technologies were, not because they're complex in and of themselves, but because we're operating in an environment of increased data and communications and cybersecurity risk. And that adds a layer of risk to the integration and implementation of any of these technologies that needs to be taken into account as we work through what the potential solutions are. So what are the scenarios that we considered? We spent a lot of time discussing amongst the team all the varying ways in which we could try and forecast the future. And actually we came to a view that there was no point trying to forecast it, because the one thing that we were certain of is that whatever forecast we came up with, it would be wrong. Not because anyone did their job properly, but these things always change. And what we wanted to do was to develop a framework or a solution space that said within that solution space, the likely outcome will emerge. And individual participants may advocate for different versions or different areas within that solution space, but we wanted to know that our roadmap was able to accommodate that full solution space. And that solution space looks like this. Very simply, it's 4 scenarios. We said that when we look at all the things that can change, it comes down to 2 key variables. The first is how centralized or decentralized the power system is. The second one is how much you rely on essential system services coming from conventional generation versus those services being provided by a range of other sources. To put that in very simple language, scenario 1 assumes that we have very high levels of centralized PV and some wind, modest growth in distributed PV, but it assumes that for periods of time, the engines in Alice Springs are actually turned off. That's a pretty scary thought for some people, but we wanted to put it out there because it's a possible scenario and it provides a boundary condition under which we can assess. Likewise, scenario 2 assumes that engines are off, but also assumes that it's occurring in the context of there being higher levels of distributed PV and smaller levels of centralized. Scenario 3 and 4 have that same split between high levels of centralization versus low levels of centralization. But in these scenarios, we assume that in all cases, we always have some synchronous generation operating to provide essential system services. By utilising these scenarios, we were able to then build up some fairly complex techno-economic models that looked at how that actually worked and how we would actually dispatch the power system of the future. These dispatch models actually broke the power system down in 5-minute intervals for an entire year, creating Monte Carlo analyses of real-world weather data and real-world load data, and then actually dispatched every single engine in the power system, as well as every single wind and battery that we modelled in there to work out how it would actually work. This graph in front of you is just one image of one day of one scenario where we looked at how might the power system actually be dispatched over the course of that day. In this particular scenario, we've assumed that engines have stayed on, but we've also assumed that there's large-scale batteries and centralised wind and centralised solar, as well as behind-the-meter PV going to load and to the grid. And you can see that actually the solution we're trying to solve for is to balance all of these components together. Ultimately, the power system of the future is very much like the power system of today, in that whatever we do next week, each second we still have to balance supply and demand, and that requires a whole bunch of things to work together. We didn't just do the techno-economic modelling in the context of trying to work out what the costs were and how those things work together. Underpinning that was a significant body of power systems engineering work that sought to understand what the strengths and the weaknesses were in the grid, what parts of the grid were going to be constrained at different cases. As you can see in this particular model, that in this particular case, there's a red highlighted area. I'm not going to dive into the technical details of what that case is, but it highlighted that in some of our dispatch models, as they were coming out of the techno-economic analysis, it highlighted then constraints in the power system. That didn't become a binary, we can't do that or we can do it. What it did do it was to say, yes, you can do it, but you need to consider these other things. While we have a generally strong network, what became apparent is just how sensitive the network comes under certain contingent scenarios, particularly through those very low load environments. The models actually also then went through and looked at a whole range of different energy storage use cases and modelled out hundreds of behind-the-meter PV systems operating stochastically, but all with different energy storage use cases, recognising that different consumers will themselves use their batteries differently over time. And we needed to be able to make sure that the modelling properly recognised how those things were going to be there. We couldn't rely on all consumers doing all the same things all at the same time, because if the investment model for the power system relied on it and consumers didn't, then we would be in trouble. So having that broad reflection of how consumers would work at the behind the meter was just as important as seeing what the dispatch behaviour would actually be at a central level. So what were the key insights? All of the scenarios we modelled were technically viable. And this is really critical. 2 out of the 4 cases we considered assumed that we will, in a regulated grid, turn off the engines for periods of the year. And it was proven to be technically viable. Sure, there's things that we need to do to address that, but we were able to demonstrate that it was technically viable. All 4 of those scenarios recognised that we needed substantive investment to be able to achieve that outcome. The net present cost of that investment was in the order of 186 million plus or minus 15% across those 4 scenarios. So actually within the sensitivity that we could do, very consistent response coming out. Most importantly, all of these scenarios highlighted that there was a significant investment required for enabling technology. Depending on whether or not that enabling technology is more focused on centralised essential system services or decentralised, does change some of the cost assumptions. But there is a material requirement for enabling technology to be able to support the uptake of renewables elsewhere in the power system into the future. We did undertake a body of work around what all the opportunities for gas savings would be through centralised generation. We have been asked by a number of people as to whether we've done forecasts as to what the future cost will be in tariffs. We very explicitly steered away from that because tariffing and the different models that may appear there are highly dependent on the sensitivity of the economic conditions at the time. So the focus was really on the net present cost to give us a baseline comparison as to what the investment cost would be. But there are material savings to be made. There's the savings associated with the gas there. There's also, we have not taken into account potential savings associated with carbon credits or carbon, any implied or implicit or explicit carbon pricing that may occur in the future. We have recognised and split out within the analysis the split between public sector investment that has to occur only by public sector entities versus public sector investment that may occur through things like PPAs via centralised renewables versus private sector investment that's occurring behind the meter, and to try and understand how we get that and still maintain security and reliability. That modelling gets pretty detailed pretty quickly. I'm not going to go through all of it right now, but we have highlighted in the report these 4 key scenarios and some sensitivities to that look at the different orders of magnitude that are there. As I noted before, cases 1 and 2 assume that there are periods of time where 0 synchronous generators will be operating, whereas cases 3 and 4 assume that there will always be a minimum of 3 synchronous generators operating. In all 4 cases, we achieve 50% renewables contribution by 2030. That's 50% renewable energy, not just instantaneous power. You can see then, though, that those different scenarios have quite different scaling in the amount of behind-the-meter PV, be it controllable or uncontrollable. It also shows the different amount of centralised renewables that are there, be it solar and, in one case, wind, and notably the different levels of energy storage that are required, both at a small scale and a large scale, and separates out both the megawatt hours of storage from the power requirement. The power requirement is a really critical part of this equation, particularly in the context of recognising that 2 of the 4 scenarios assume that engines go off, because the power is what enables us to respond to the instantaneous faults, and so that becomes a key determinant of the sizing of our batteries. We broke those costs out, and we can see some of the costs that are there, that these are not direct capital values. These are the net present cost factored out over the life of the assessment period, and shows that in these cases, in scenario 1, we actually turn the engines off for up to 1,500 hours a year, which is pretty significant, and scenario 2 for 500 hours a year. Some of you may notice that the gas savings are actually slightly lower for the one that has a higher gas off period. And while that might seem counterintuitive, it actually comes down to the efficiency of the gensets in the periods of time where they are operating are actually reduced in that large-scale VRE deployment case. And so we don't see quite the same saving that might otherwise be assumed. So all of that's very exciting and very interesting, but what do we actually do with that? Well, the roadmap mapped out actionable pathways and near-term priorities to try and work out what we could do. And these are broken down into 3 key phases of the transition. Number 1, secure the system. Number 2, do all of the planning and the operation works that we need to get there. And then number 3, accelerate that renewables deployment. Secure the system is really what we need to do between now and 2025. In fact, we're probably now and the end of 2024. It's the next 12 to 18 months of work that's ahead of us. That advanced planning and operation work is that period from 2024 out to maybe 2027, 2028. But the reality is at the end of that period, substantive investments in new technologies will need to be made, and we need to be able to be ready to support that deployment by 2028, such that those technologies are commissioned and enabled to run by 2030. So they're the 3 phases that we've actually mapped out. We've broken that out into the roadmap in far greater detail, looking in that security of the system of getting focused on emergency distributed PV management, battery energy storage system procurement and design and procurement and deployment activities, doing a lot of work around protection system analysis and redesign, which is boring to a lot of people, but it's critical because it keeps the power system safe. We need to be planning and accelerating new bulk load connections, and then really getting prepared for that essential system services plant and being ensured that we're able to design and procure that into 2025. These are the actions that we need to do to secure the power system. That advanced planning and operation takes us to the next step, where we start to get into probabilistic forecasting that allows the power system to be operated on a statistical basis of where things are, not where they just were on a deterministic basis. Moving into designing, developing and procuring advanced power system management systems that enable the coordination and operation of distributed PV. Deployment of dynamic PV export management, and then operating under a sort of a continuous review of centralised and decentralised renewables uptake. That requires ongoing analysis of other low carbon resource mixes and where those things are moving, and also considers what steps may be able to be taken to be able to support more rapid uptake if the uptake is not aligning with forecasts that are there. Finally, we need to accelerate, and that accelerate needs that large-scale solar and wind generation, most notably solar. And wind is a possibility, but it's probably the last of the projects to be deployed, because under all the scenarios we see, going through the development and the firming process for large-scale solar is absolutely vital. We recognise there may be a couple of rounds of those activities, and so you can see those mapped out. We see that there may be opportunities for substantive support and direction through public housing trials, for example, such as the one that we've already conducted in the Alice Springs Future Grid project, as a mechanism to drive larger scale DPV deployment. And then implementing zero gas periods for those cases where we're reliant on that, where we develop and trial those processes in the period of 2026 to 27, and then move to a standardised operation and evaluation process into 27, 28, 29. The roadmap, as I'm sure you can imagine, is a very substantive document and goes into far greater detail about each of these actions. But fundamentally, those near-term priorities lead us to developing sort of formal responses to the 2030 roadmap, establishing cross-organisational transition processes and securing that funding. We have been meeting with all of the key stakeholders that we need to engage with on this project over the last couple of weeks to be able to brief them on the consequences and where this report is going. As we move to finish off this presentation and move to some Q&A, I really want to close by acknowledging the significance of what's been done. I've done a poor job of trying to wrap up 2.5 years worth of work in the last 45 minutes. But it has been a significant piece of work that have required a large group of entities to work together in ways that they haven't always been used to having to do. But they have done so willingly, and they have done so at times under very tough conditions, because the project has had people operating in places all around the country due to COVID and often not being able to meet together when we would have hoped. They've done so at significant expense. The aggregate expenditure of the parties of their own contributions is nearly $5 million. And that's significant. And that's coming from different entities who've committed, even as the project has had to undertake additional costs to get to the end. But it's also important to recognise there are individuals involved in this, and I'd like to specifically acknowledge the individual sub-project leads. Hannah Farrow, who's been with the project since the start, managed to have a baby and get back to work before we managed to get the roadmap complete. Chaitanya Meshram, who's been a critical part of enabling our compliance and the oversight of the project overall. Josiah Fajardo, who led sub-project 1, Paul Rodden, who led sub-project 2, Perina Landini, who led sub-project 3 and worked on sub-project 4 as well, and Thomas Wern on sub-project 5. They all represented their different entities well, and represented them significantly, put a lot of hard hours in, along with all of the different partners that worked in it. But the roadmap itself was developed with a dedicated project control group consisting of representatives of Acustica, CSIRO, Power and Water and TGen, and they worked diligently to be able to get to this point. The point we've got to is a roadmap that I think is comprehensive. It is honest in recognising the challenges we face. It is realistic in accepting the requirements and the need for change and the changes to consumer expectation, and provides plausible pathways to the future. We think the roadmap is a seminal piece of work that we hope many will be able to see and utilise, both for the future of the Alice Springs power system, but importantly for the future of power systems across the Northern Territory and the rest of Australia. Thank you very much for listening to me drone on and coughing occasionally. And with that, I might turn off my screen sharing so I can see you all, and then we can go back to some Q&A. Thank you very much.
Excellent. I'll take 20 seconds to have a drink as well. Appreciate the struggle you've gone through to present that. Thank you very much.
Sorry, Gavin, we're unable to hear you, unfortunately. I'm not sure if you are speaking or not. Sorry, we're still not getting anything from the Corkwood room, unfortunately.
All right, hopefully. Okay,
No, I think you've got two microphones going on in that room. While we're waiting, I might just go to Q&A in a less structured manner. And Jane, you've got your hand up first, so you get to ask the first question.
Yeah, I just wanted to jump in. Thanks so much, Lyndon. That was a fantastic presentation and exciting work. I just had a question about the diesel off models. I think you said that it was projected that there was 1,500 hours that the gas or diesel wasn't being utilised, but that it still wasn't the most cost effective, like it still came out as the more expensive scenario. Is that because of existing contracts, or is that the inefficiency of the generation going on and off?
Yeah, so look, it's a great question. I might just ask anyone when they are asking a question, if you can just introduce which organisation you're from as well, just so everyone else knows. But it's
sorry,
yeah.
I'm from DQ and I'm in the electricity division.
No worries. Yeah, so it's one of those things which seems counterintuitive when you first look at it, but once you start getting under the hood of it, it becomes a little bit more obvious. No, it's not as a consequence of contracting or any existing arrangements that are there. It's simply that in that scenario where and that was the scenario one where it's high levels of centralised PV and going with engines off, you end up in a circumstance where to do that, you have to have a large amount of storage to be able to deal with the changeover in the middle of the day for that bulk storage. The consequence of that is that you're still, when you are running the machines later on, you're not necessarily running them most efficiently because you've moved so much energy that's then got to be deployed over the course of a number of hours from the batteries. And so you're just running the engines at a lower level of efficiency for a longer period in that particular model. And so it comes down to that trade-off between how you, when you do have engines on, you have to have 3 of them on. When they are running, you need to have them minimally loaded, but that's less efficient, and then you're trading out. It shouldn't be read necessarily that is the least economically efficient outcome. It just recognises that the gas savings with that particular model are not necessarily as large as what other people may assume.
Yeah, hey, Lyndon. Yeah. Well done for pushing through the dreaded lurgy that a lot of people are fighting. Yeah, just a quick question. Has the Alice Springs Future Grid taken on any learnings from the NEM? That, you know, generally I think we've seen a fair bit of this come out with a few retailers around the country. So are you trying to sort of do the findings yourself, or you're taking references from what's been happening on the NEM probably for the last few years? That's a question.
I think just in order that question around NEM learnings into the project, yeah, absolutely. You know, we're sort of seeing what, you know, in the broader project as well, just seeing what is going on in the NEM and then feeding it back into our own project. There are a few sort of like quirks in our own network that has meant that we haven't always, you know, sometimes we're a bit ahead, sometimes we're a bit behind, but absolutely no, I think the work here is relevant to those other jurisdictions.
Yeah, thanks for that. Cheers.
Anyway, I don't know if there's...
Yeah, I'll just try and see if there's like any questions online as well.
Yeah, it doesn't seem like there's too many. Oh, yeah, we've just got a few now.
So Peter Kilby, if you're still online.
Yes, did you want me to come off mute?
Sure, thank you. Just state where you're from.
Energy Queensland. I was just interested in that timeline. I saw that the PV backstop developments were proceeding very, very soon, but the dynamic management of PV looked like it was out towards 2026, and I was just wondering why that wasn't commencing sooner.
Yeah, I guess it is somewhat ongoing in the background already as part of works already ongoing, you know, probably with Power and Water Corporation as well. I think it's more, you know, any necessary changes to standards or regulations or other such sort of compliance work would be happening later, and
Lyndon's back on, so we could probably repeat that question as well if you like.
He'll give you a different one. Answer.
Okay, thanks. Hi, Lyndon. Peter Kilby here from Energy Queensland. My question was just around the timing. I saw that PV backstop was being implemented ASAP, which makes sense given the imminent minimum demand constraints. But I was interested in why dynamic PV management wasn't looking like it was commencing until sort of 2026 or something on the timeline.
Yeah, look, a really important thing to note is that it's not that any of these dates can't occur earlier, but they're the latest dates by which they need to occur in order for you to still be able to follow on that trajectory through to 2030. So that's, if to the extent that there is enthusiasm and interest in being able to progress those earlier, then we would absolutely support and advocate for that. I think it is worth noting that there are elements, one of the great strengths, but also one of the great weaknesses of Alice Springs is the cohort of early adopters. And so we have a larger fleet of older solar systems here than may exist elsewhere. And that's because it goes back to contributions in solar cities. A lot of those older inverters are not able to integrate with some of those dynamics solutions that are available now. We have demonstrated and have got trials of those dynamic solutions that are underway with the new battery inverters that are coming out, and they are being implemented. But it's that sort of threshold criteria around mandating that people, we don't want to be in a position where we're forcing perfectly good solar systems to have to go and undertake an upgrade. And so it's then a question of what's the timing of that to facilitate those over time as the deployment actually matches that. Hopefully that answers the question.
Yeah, thank you. That align our experience with upgrades is they're a nightmare, and it's very much about catching as many of the new systems as quickly as possible.
Yeah.
Thank you.
Yeah. So for us, yeah, that 2025, 26 period is really the deadline. If you don't have it implemented there, you'll miss the boat because you'll just too much it'll gone past. Tim Ryan, I think you're next.
Yeah, there's a couple of questions from Tim. Tim, you can come off mute and ask them, or I can relay from the chat. Up to you.
I think I'm off mute now.
Yes.
So I'm not sure. I think I might ask them in the wrong order. But where does smart metering, monitoring, consumers actually having access to real-time data? Where is that fitted in your work so far?
Yeah, so it's important to note that we haven't tried to solve every one of those technical issues in the work. We recognise that smart metering is a part of that, and different devices and different entities will advocate for different customer solutions that may exist there. What we've said is that the technical solutions we're proposing are a minimum requirement. So being able to integrate with the power system, we trialled both software and hardware integrations for behind the meter PV. We had differing levels of success with that. I know there are entities who are actively advocating for inverters that are able to communicate with a smart meter and use that as a mechanism to get data. There are others that are proposing monitoring solutions that exist entirely separately from those. We haven't formed a judgment as to having to choose one or other of those technical solutions, rather recognising that the characteristics of the solution must include that level of control into the future.
Have you seen the AEMC's power of choice metering review, in particular the mandate therein that consumers should have access to real-time data behind the meter or their devices or innovation?
Yeah, absolutely. And we don't have the way, though, that AMC rule change works or proposed rule change works doesn't necessarily directly apply into Alice Springs or the Northern Territory. Notwithstanding that, we don't have any objection to it. We see it being as something that's complementary, but it's not something that either stops or accelerates work that is necessary. We've tried to describe as best as we can the characteristics of the solutions without necessarily mandating that it must be reliant on one particular solution or another.
No, I think that's right, Lynn. And certainly you don't have to, at the moment, as far as the power of choice under that captured heading of what it was all about was excluded the Northern Territory, WA and Victoria. But that broader aspect of how using a smart meter as a reference point for equipment behind the meter or data systems there for disaggregation and flexibility, etc. I think it's hoped that would apply Australia-wide so that innovation can be used at the technical.
Yeah, look, we're entirely open to that. We weren't trying to design or engineer those solutions, but we were trying to give consideration to how they might work. Did you have a follow-up question before I go to Dave?
Yeah, just a quick. The other one was asked about the VPP project. Was that VPPs tend to be very orientated around demand response type operation as a peaking plant, but it looks to me from all your charts, etc., that the real challenge is demand management and temporal shifting of load, etc. And I was wondering if your VPP work focused on that demand management, temporal shifting type work, or whether it was really just a traditional VPP.
No, it was very focused on looking at how we could optimise the charging and the discharging of the behind-the-meter batteries, utilising a tariff structure that would most benefit the grid, particularly at those periods of time where we had minimum demand. And it was then became a conversation around the extent to which you rely on tariffing structures, which are by necessity a little bit more static than control systems. How much do you rely on those versus having something like dynamic operating envelopes, and what is the right mixture of those two capabilities to achieve that outcome?
Did your dynamic operating envelopes work include using price when
No.
signals? So you didn't really include the other half of DOE where price signals can be sent for non-conformity.
We were not trying to prove that the system, whether it works or not, because we know there are trials underway to prove that. What we're trying to understand is what is the value opportunity in the context of a power systems like the Territory, and then how do you actually think about the implementation of that? So we have certainly recognised that there is absolutely a role for consumer-based VPPs. We also recognise that there is a significant role for hardware and software-based network implementation of dynamic operating envelopes. The spread of those, I think, is ultimately something that, as the design and engineering of the different groups proceeds, is able to work up the right solution for that. But it's not something that's definitive, and we're not going in saying, well, the solution is VPPs or the solution is DOE or something else by itself.
Did you do any work on community batteries? I know you've had a lot of discussion about behind the meter batteries, but as many people on this call will probably know, I'm pretty leery of behind the meter batteries instead of having community batteries, which you know, use the network infrastructure to facilitate better storage and make sure that that service is available to everybody, not just people with rooftop solar.
Yeah, look, I will answer this question, Tim, and then I'll sort of move on to others, just because recognise that there's probably a few other questions. But yes, we did have a 300 kilowatt battery, and it was operating and could be considered in the context of being a community battery. We didn't actually run a dedicated consumer trial with community batteries. We recognise that there are trials underway elsewhere. We're not. If we look at the modelling work that we've done, it recognises that the centralised batteries that are required need to be spread in different locations throughout the network. They can't all be located in one location, otherwise it creates some of the contingency issues that already exist. But they could exist as larger batteries in a zone substation, or they could potentially include smaller batteries in distribution areas as well. I guess we were deliberately trying to avoid a circumstance where we were doing a detailed design of a future power system and trying more so to create the opportunities in those boundary conditions so we could understand where we're operating to.
Fantastic. Thanks very much.
David.
Well, you can see I'm a Luddite here, but that's okay. Just on the very basic stuff, noting that then with, between 10 and 2, it seems like that's when all the solar kicks in. And should an organisation like us that's taken the step of trying to get some plug-in electric cars at the first step, should we be encouraging staff to plug in between 10 and 2 and stuff like that even make any difference at all? Or to,
Yep. We're probably not quite at the point of encouraging to plug in electric heaters in the middle of the day, but certainly one of the bits of work that is in the report is consideration around the role of EVs, and particularly what is the distribution of charging opportunity that may emerge out of that? How would you need to control that? And what limitations may need to be placed upon it? We see EVs being part of the solution. I know there are some who would advocate that EVs with vehicle-to-grid charging may be a very big part of that. We haven't necessarily come to that view, not because we're anti-EV in any way, but we recognise that there's progress in take-up of that. But the model and the way we've built out the roadmap is to recognise that something like EVs, and particularly with future vehicle-to-grid, requires control and integration. And if you're going to have control and integration, you have to have the systems behind it to be able to make sure that it works properly. One of the things that we're very conscious of, and noting that we've got Dave Hayes and Jamie online, that it's all very well and good to have a really complicated power system with everything that does all these wonderful things, but if Optus goes out, as we've all experienced over the last week, and things stop communicating, the power system's still got to run. And so how do you actually make that stuff work? How do you solve that? That's the tricky bit. And it's the job in front of us is to solve those things, and some of that's different communication paths and so on. So it's the question isn't whether or not it is EVs, it's more about, well, assuming that it is, how would you integrate it? And the same types of integration systems are going to be required for whether it's EVs or behind the meter PV, or if it's community batteries. Jane, back for a second shot.
Sorry if you already touched on this, but I was wondering whether there was any modelling on the any tariff design to incentivise the load shifting to the daytime use to take up that renewable generation.
Yeah, so we did undertake some work in this, and a part of the work led by Jacana in the trial of the overall Future Grid trial was looking at different tariffing structures that may support that. Particularly in the context of the VPP and behind the meter solar and battery. I think what emerged out of that was a body of work that Jacana are continuing to look at that requires further analysis on it. As part of the roadmap, we haven't made explicit recommendations as to what those tariffs should be, but there is clearly work needs to be done under that. I think the key concern that sat with us is that it's very easy, particularly in the context of a community such as Alice Springs, where we have quite divergent levels of socioeconomic demographic groups to come up with a solution that suits one group, but could actually have misaligned impacts or unintended consequences for other groups. And so being able to work through that is a key part of it. And Jacana have given consideration to that, and as I understand it, are continuing to work in that space. Jamie.
Yeah, g'day, Lyndon. Yeah, look, start off with, I think that's a very interesting presentation. Yeah, look, and that's why I sort of asked the question, will it be publicly available on the website? Because there is some very interesting statistics and that with that. Like you said, you've realised this is a very complicated and unique grid here. In the 19 years I've been working as an operator here at the Ron Gooden Power Station, I've seen significant change within the grid and the load demand in that. I suppose it's just some more points. As I say, that's a really good presentation, and I think it should be made available. But there's some good points in there, and you've recognised some good points. You know, I think you've got the right attitude in the fact that you're not going to be able to solve all the problems moving forward, and the fact that if you've got a group or a body that has the ability to deal with future known and unknown issues and to be flexible to deal with things, that's a step in the right direction. Also, too, I'd suggest if you look at the Queensland government has released what is it? I think it's a $60 billion jobs and energy plan, and there is some really good points in that that we could we're looking at adopting within ourselves within the ETU. We want to roll out here in the territory, but you know, we're focusing on, you know, technology and renewables and things like that. But we need to be cognizant of too is that having skilled personnel to operate our system. You know, I mean, we've seen what happens when we centralise control. You know, and we had that outage of 16th of October 2019. No one wants to go there again, and we do. We want a safe, reliable power supply. So a transition to that we see as having our personnel involved in that. You know, and I think, you know, these future developments, we need to be working hand in hand with our major energy providers, Territory Generation, because they, even though it is an open market grid, Territory Generation is a generation provider of last resort. So when everything goes out, we're the ones that get it going again. So yeah, they were just some points I'd like to make in that, and I found the presentation very interesting. Thanks.
Thank you, Jamie. And look, we will, as Gavin mentioned previously, the actual report and everything that is in the slide deck that I've just shared is contained within the report. So all the images and stuff are straight out of that. The report is in final stages of being published and being ready for publishing. So this is effectively you're getting the inside goss to what that report's saying, and we're anticipating that report being up on the website within the next 2 weeks, and will be available for people to download and review. And you can read all of the different analysis and text, and I'm sure we'll get the various critiques of it at that point.
Yeah, no, it's good.
And this video will be shared via the website as well as the report. Yeah.
Yeah. Next question.
There's no more online, but if somebody would like to raise their hand or come off mute, we do have around 6 minutes left. Steve Morton.
Yeah, thanks, Steve Morton from DKRI. Thanks, Lyndon. That was great. You mentioned reinvestment required for the next phase of integration. Are you talking new money, or is this a redirection of an existing flow of funds into the energy system?
So I think it the word reinvestment there was perhaps in framing it in the context that there's often an assumption that we've invested in the power system already. So why do we need to invest more? But the reality is we need to continue to invest into the power system. It is a complex machine, and we've got to keep that thing running. Some of it's are physical machines, parts of it are more ephemeral, but it is a complex system. And so it does require investment and will require new investment to be able to support though both stabilising and securing the power system, but also being able to support its direction into the future.
All right, there's no new questions online and there's no hands raised, so we could give people a few minutes back if they want to have a coffee or run off to dinner if they're in a different time zone. But we will thank everyone for their time. Thank you for attending. We hit 80 people plus the people in this room, so it was a good attendance. As noted, this presentation will be shared on the Alice Springs Future Grid website, and we'll make sure that it's also shared through Arena. Please note that there are other knowledge sharing artifacts from this project on the Arena knowledge sharing portal. So if you just look up this project, Alice Springs Future Grid on the Arena site, you can click on the knowledge sharing articles there. And then will be other content that is shared as part of this project through the project's website. Thank you, Lyndon. Thank you everyone for attending. Thanks for your time this evening and this afternoon, and take care.
Thank you, everyone.
Thanks.